Hello everyone, welcome to a special episode of Math-221. I am going to make the practice test 2 solutions and I'm going to talk you through the solutions while I'm making them. So let's get started. Okay, so first let's just go over the instructions so I make sure that you understand. The real test 2 will be similar to this practice test, but it'll be shorter. And so for each part that I'm going to go over, I'll tell you how many questions there will be. The test is going to be open notes, open book, and open internet. However, you can only talk to me about the questions. This means you cannot post the questions on the internet. But you can read whatever is already on the internet or watch videos or whatever, including this video. Okay, so let's look at part 1, which is algorithms, loops, and pseudocode, and there will be one question similar to this on the real test. Okay, so we just have to fill in the trace table for this algorithm. So I made the table for you, and if you do it correctly, then you should need exactly the same number of columns that are in the table. Okay, so the first blank here is for before the first iteration. So after iteration 0 means before the first iteration. So before the first iteration, the value of x is given right here. So you just have to copy that over here. It's 3. Okay, so now let's get into the while loop. So first, before starting the while loop, we have to check whether the condition is true or not. So is x greater than 1? Well, 3 is greater than 1, so yes. So we are going to execute the while loop. Okay, so now we come to an if-then. So we have to check this next condition here. If x is odd, so that, in this case, 3 is odd, so that is true. Okay, so we're going to go ahead and do the then part. So x is going to be redefined to be 3x plus 1. So 3x plus 1 is going to be 3 times 3 plus 1, that is 10. Okay, and then we do not do the else part because that is what you would do if the if part was false. So we don't do that part. Okay, so then we're done with the while loop. So we come back and try to check the while condition again. So let me just erase this stuff here. Okay, so now we're going to come up to this part again and check the while condition. So currently x is 10 and 10 is greater than 1, so we are going to execute the loop again. And now we're going to check the if condition here, if x is odd. So in this case that is false, x is not odd. So instead of doing the then command, we're going to do the else command. So we're going to do this. So we're going to define x to be x divided by 2. So that is going to be 10 divided by 2. That's going to be 5. Okay, and that's it. So now we will come through and check whether we should do the while loop again. Okay, so we go back up here and we check whether this while condition is still true. So 5 is greater than 1, so that is true. So we're going to do the loop. And now we check the if condition here. Is x odd? Currently x is 5, so yes, that is odd. So we're going to do this then part. Okay, so x is going to be redefined to be 3x plus 1. So 3 times 5 plus 1, that is 16. Okay, and that's it. We don't do the else. So that takes us through that loop, and now we're going to go up and check the while condition again. So x is currently 16, and that is greater than 1, so we're going to do the loop again. And now we check the if condition, if x is odd. This time x is not odd, so we're going to do the else. So we're going to redefine x to be x over 2. So 16 over 2, that is 8. Okay, and that's it. And now we will check whether we can do the loop again. So we come back to the top, check the while condition. 8 is greater than 1, so we are going to do the loop. And now we check the if condition. X is not odd, that is false, so we're going to do the else. So we're going to do x is defined as x over 2. So that's 8 over 2, that's 4. Okay, and just again, we're going to come back up to the top and check the while condition. So 4 is still greater than 1, so we are going to do the loop. If x is odd, that is false, so we're going to do the else. So x will be x over 2 again. So we're doing 4 over 2, which is 2. Okay, and then one last time, we're going to come up and check the while condition again. And 2 is greater than 1, so we're going to do the loop. Then we check the if condition. X is not odd, so we're going to do the else. Okay, so x is going to be defined as x over 2. So 2 over 2, which is 1. Okay, and then you know that you're supposed to stop now because you got to the end of the table, but I mean, actually what happens is that you come back up to the while condition and you check the while condition one last time, and now you're checking whether 1 is greater than 2, and that is false, so that means you stop doing the loop. And that's it. Okay, so let's do this one. It has 2 different values. So before the first iteration, A and B are defined right here. So these you just copy them over there. So this is going to be 4, and this is going to be 2. Okay, and now for the next column, we're going to check the while condition. So while A is greater than 1, so in this case, A is 4, so 4 is greater than 1, so we are going to do the loop. And now we check the if condition. So is B greater than or equal to A? That is false right now because B is 2 and A is 4. So we're not going to do the then, we're going to do the else. So A is going to be redefined to be A minus 1. So this is going to be 4 minus 1, which is 3. And then nothing happens to B, so B is just going to stay the same value, which is 2. So we're just going to transfer that one over there. Okay, and that was the first loop. So now let's go back through and check the while condition again. So we check the while condition again. A is still greater than 1 because A is 3, so that is true. So we will do the loop. And then we check the if condition again. So is B greater than or equal to A? That is false because B is 2 and A is 3. So again, we're going to do the else. So the else tells us to redefine A to be 3 minus 1, which is 2. Okay, and then once again, nothing happens to B, so B just gets copied over. All right, and then we're going to check the loop again. Okay, so we check the while condition again. A is still greater than 1, so we are going to do the loop. And now we check, is B greater than or equal to A? So now this is actually true because they are both 2, so that is true. So we'll do the then. So for the then, B is going to be redefined to be B minus 1. So this is 2 minus 1, which is 1. And this time nothing happens to A, so A just gets copied over, so that'll still be 2. Okay, that's the end of the loop, so we'll check again at the top. So is A greater than or equal to 1? Yes, that is true, so we are going to do the loop again. And then we check, is B greater than or equal to A? And this time that is false. So we're going to do the else, which is A equals A minus 1. So A is going to become 2 minus 1, which is 1. And nothing happens to B, so this just gets copied over. Okay, and then we're going to check the loop again. So we check the while condition, and this time the while condition is false. A is not greater than 1, so that is the end of the loop. Okay, last problem of this type. So before the first iteration, we just copy these values of R and Q over. So this is going to be 25, and this is going to be 0. Okay, so now we're going to check whether we can do the loop. So while R is greater than or equal to 7, so currently that is true, 25 is greater than or equal to 7, so we are going to do the loop. Now we check the if condition. So is R times Q less than 12? Currently R times Q is 0, so yes, that is less than 12, so we will do the then line. So Q is going to be redefined to be Q plus 1. So this is going to become 0 plus 1, which is 1. And then nothing happens to R, so R will just get copied over. Okay, that's the end of the first iteration, so we check the loop again. Okay, so we check the while condition again. So R is 25, which is still greater than or equal to 7, so we will do the loop. And now we check, is R times Q less than 12? So currently R times Q is 25, which is not less than 12. So this time we're going to do the else condition. So we're going to do R equals R minus 7. So this is going to become 25 minus 7, which is 18. And nothing happens to Q, so Q is just going to stay 1. Okay, now we check the while again. So R is 18, which is greater than or equal to 7, so we will do the loop again. And now we check, is R times Q less than 12? R times Q is currently 18, so that is not less than 12. So we will do the else part. So we just subtract 7 from R again. So this is 18 minus 7 equals 11. Okay, and then nothing happens to Q, so this is still just 1. All right, now let's check the loop again. So the while condition, r greater than or equal to 7, that is still true because r is 11. So now we check the if. R times Q currently is 11, so that is true. So we will do the then part. So Q is going to become Q plus 1, so this will be 1 plus 1, which is 2. Okay, and then nothing happens to R, so this just stays 11. Okay, now let's check the while condition again. So R is still greater than or equal to 7 because R is 11. So now we'll check R times Q. So R times Q is currently 22, so that is false. The if condition is false. So we're going to do the else part. So we're going to define R to be R minus 7. So this is 11 minus 7, which is 4. And then nothing happens to Q, so that stays 2. Okay, and now we come up and check the loop one last time. The while condition here is actually false now, so that is the end of the loop. Okay, let's look at part 2, sequences, summation, and product notation, and there'll be 2 questions similar to these on the real test. Okay, so we're going to calculate the sums and products. So you just have to remember how the notation works. So for number 1, we're doing the sum of from I equals 2 to I equals 5 of the formula 2i plus 1. So all you're doing is you're just plugging in the values I equals 2, I equals 3, I equals 4, and then finally I equals 5 to that formula, and then you're just adding it all up. So this is just going to be 2 times 2 plus 1. So that's the first value here, goes in the first one. And then you do the next integer, so that'll be 2 times 3 plus 1. And then 2 times 4 plus 1. And then you stop with the value that's on top of the sigma. So 2 times 5 plus 1. So that's this last one that goes here. Okay, and then you just add that up. So that is, let's see, 5 plus 7 plus 9 plus 11, which is, let's see, 9 plus 11 is 20, 32. So it's a 32. Okay, so that's that. And then number 2, the same way, you're just plugging in all the integers from k equals -2 up to 2 to this formula. And this one involves a fraction, so might need to do a little more work. So we start with k equals -2, and then we do k equals -1, and then we do k equals 0. I'm sorry if you guys can hear my cat banging on the door. He gets really mad when he's not allowed to be in these videos. Okay, and then we stop when k equals 2. Okay, so that's it. So it looks like I actually made a mistake here because, as you can see, this is going to be undefined. That one is undefined. So this whole thing is going to be undefined. Sorry about that. That's what happens when you're not thinking. But anyway, that's how you would do that normally. Okay, so for number 3, it's the big pi sign instead of the big sigma. So sigma is Greek S for sum, and then pi is Greek P for product. So we're just going to do the product from j equals 2. J equals 2 to 6 of j over j minus 1. Looks like I accidentally made the same mistake in this one, and we're going to get undefined. But let me just show you how you would do it anyway. So you just plug in 2 for the first one for j, and now you're doing a product, so this is multiplication, not addition. So this is going to be 3 over 3 minus 1. Oh, actually, I didn't make that mistake. We don't get an undefined. Oh, that's good. I guess I was using my brain for at least part of this. Okay, and then times 5 over 5 minus 1, and then times 6 over 6 minus 1. Okay, so then we can just simplify this. So this will be 2 over 1, 3 over 2, 4 over 3, 5 over 4, and then finally 6 over 5. And then we're going to get a bunch of cancellations. So let's see, cancel, cancel, oops, cancel, 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 cancel. So this is actually just 6. Okay, and then the last one, number 4. So same way, just doing the product from n equals 0 to 3 of 3n minus 1. And so I'm going to plug in 0 first, so 3 times 0 minus 1, and then 3 times 1 minus 1, 3 times 2 minus 1, and then 3 times 3 minus 1. So this is, let's see, the first one is -1, and then 2, and then 5, and then 8. Okay, so this is going to be, let's see, 10 times 8, 80, -80. And that's it. Okay, so now we're going the opposite direction. So I give you a sum or a product written like this with the ellipses, and then I want you to put it into summation notation or product notation. Okay, so what I want you to notice about number 5 is that this is odd numbers. So the form of an odd number, you can always write it like this, can be written as 2k plus 1. And then you just need to figure out what k is for the first odd number and what it is for the last odd number, okay? So this is going to be the sum of 2k plus 1 from k equals something to something. So what does k have to be in 2k plus 1 to give you 1? It has to be 0. Okay? And then what does k have to be in 2k plus 1 to give you 89? So the 2k part would have to be 88, so that would be 44. Okay? So to just explain again, when k equals 0, 2k plus 1 equals 1, and when k equals 44, 2k plus 1 equals 89. Okay? Right, so for number 6, it's very similar, except instead of odd numbers, we're looking at multiples of 3. Okay, multiples of 3. So multiples of 3 can be written as 3k for some integer k. So you just have to figure out what k is for the first term and what it is for the last term. So this will be sum from k equals something to something of 3k. So for the first term it's 3, so that would be when k equals 1. And then for the last term it's 99, so that would be when k equals 33. Okay? And then let's see, for number 7, so 7 is a product, but other than that it's really the same way. So this is even numbers. So even numbers can be written as 2k for some values of k. So again, you just have to figure out where the starting and stopping points are. So this is going to be 2k. Alright, so for the first one, which is 4, oops, I'm sorry, it's not a summation, it's a product. Okay, so for the first one, k is going to need to be 2 to give us 2 times 2, which is 4. And then for the last one, 50, I would need to use 25. Okay, and then let me just make a little space to do number 8. So for number 8, this is going to be, I think, hopefully you can see it's just going to be 1 over k. Alright, and then the first k is going to be 6, and then the last k is going to be 41. Okay, so let's do part 3, which is proof by induction, and there will be one question similar to this on the real test. Okay, so let's look at this problem. We're going to use mathematical induction to prove that for all integers n greater than or equal to 1, 1 plus 3 plus 5 plus ... plus 2n minus 1 equals n squared. Okay, so here is our proof. So the first thing you want to do in these proof by induction problems is always to define your p of n statement. So let p of n stand for, and then this is just going to be this part, whatever comes after the comma there. So let that stand for the equation. Okay, and then you can put quotes around that if you want, or not. It doesn't really matter. Okay, so that's what p of n stands for. So then our basis step, So part 1 is the basis step. So you want to prove P of, and then you want to do it for this, whatever this number is after the greater than or equals. Okay, so we will show P of 1, so that's using that value there, is true. Okay, so you need to state what P of 1 actually is. What is the statement that you're trying to prove? So P of 1 is the statement. Okay, so this is where people tend to sometimes get confused. So you know that you start with 1 on the left in that sum, but where do you end at? So it's always just going to be, for the basis step, it's always just the first term. And you can tell that it's just the first term because if you plug in 1 for n in that 2n minus 1 part, you'll get 2 times 1 minus 1, which is also just 1. So apparently 1 is the first and the last term of that sum, so it's really just 1. So this is the statement 1 equals, and then on the right-hand side, of course, you're plugging in 1 for n. Okay, so what you want to do is just show that the left-hand side of this equation and the right-hand side are equal. See, you haven't proven it yet, you're just saying what you're trying to prove. So the left-hand side is 1, the right-hand side is 1 squared, and then now you want to simplify that as much as you can, so that is also 1. So the left-hand side and right-hand side are equal, thus, hence, or therefore, or whatever, P of 1 is true. Okay, that's the basis step. So you showed that the P statement was true for the first value of n. And now for your inductive step, okay, so what you want to do is, what you need to show is the following. We will show that if P of k is true, then P of k plus 1 is true. Okay, so we're trying to show an if-then statement. So just like usual, we'll assume that the if part is true, and then we'll show that the then part would also have to be true. So assume P of k is true. Now don't just skip over what that means. You need to actually expand what that means. What does it mean that P of k is true? So that means, because you're going to actually need this, that 1 plus 3 plus 5 plus ... And so wherever you see n, just replace it with k. K squared. Okay, so now we will show P of k plus 1 is true. Okay, so what is it exactly that we're trying to show is true? P of k plus 1 is the statement. So we need to write this out so we can see what it is that we're actually trying to prove. 1 plus 3 plus 5 plus ... Okay, and so now you're replacing n with k plus 1. So this is 2 times k plus 1 minus 1, and then on the right-hand side, also k plus 1 squared. So you're just plugging in k plus 1 for n. So this is the statement that we're going to try to prove. We have not proven it yet. Okay. So the way these always work is you want to work with that left-hand side that is the summation. So I'm going to work with the left-hand side. So the left-hand side, LHS stands for left-hand side, is, okay, 1 plus 3 plus 5 plus ... And now what I'm going to do is I'm going to be a little bit clever, and I'm going to pull out one term from the ... You know that that covers every odd number from 5 up through 2 times k plus 1 minus 1. So you want to think about what would be the very last term right before 2 times k plus 1 minus 1. And those are all odds, right? So the thing that is changing there is what 2 is being multiplied by. So the term that would come right before the last one would be this one. Okay, the kth term would be that. And then the next one would be, oops, like this. Okay, So I have not changed the left-hand side at all. The only thing I've changed is just cosmetic. I'm now showing one of the terms that previously I had abbreviated with that ... which abbreviated a whole bunch of different terms. Okay, so the left-hand side is that. And then what I can do is, using the fact that I knew P of K to be true, what I can do is I can substitute for this whole part right here. I can substitute for that using this K squared. Okay? So that is going to go in right there. Okay? Do you see why I'm able to do that? Because I already assumed that 1 plus 3 plus 5 plus ... up through 2k minus 1, I already assumed that that was equal to k squared. So this is going to become k squared plus 2 times k plus 1 minus 1. Okay? And now I can simplify, and what I want to do is I'm going to try to show that this, which was the left-hand side, I want to show that it equals the right-hand side, which was k plus 1 squared. So I'm just going to simplify it and try to make it look like k plus 1 squared. Oops, I already wrote that, didn't I? Let me simplify it a little more. Okay, so I can drop the parentheses, and then I can distribute the 2. Okay, and now I can just factor that into k plus 1 squared. Okay, so what I've discovered is that the left-hand side I started with is actually able to be rewritten and simplified into the right-hand side, and that proves that the left-hand side equals the right-hand side. So that means that P of k plus 1, I've shown that that equation is true. Okay, and that's all you need to do. So that was the basis step and the inductive step. If you want to throw in an extra statement there at the end, like this proves that P of n is true for all n greater than or equal to 1, you can do that, but it's not necessary. So this is all the necessary parts. Okay, so let's do another one. Okay, so again, we're going to start our proof off by defining what the P statement is. So let P of n be the statement. And now I'm just going to write the equation. 1 plus 2 plus 2 squared plus dot up through 2 to the n equals 2 to the n plus 1 minus 1. Okay, so that's what P of n stands for. Now I'm going to do the basis step. So for the basis, we will show that P of, okay, so this time it's going to be P of 0, because that's the value that was in the inequality there. So we will show that P of 0 is true. In other words, we will show, so let me write out what P of 0 actually is so that we can see what it is we need to prove. We will show that, okay, so now's the part where you guys all get confused, like what exactly is on the left side of this equation. So if you plug in 0 for n, I think you will see that the last term will be 2 to the 0, which is 1. So the first term is 1, the last term is 1, that means you only have 1. Only 1 is up there. So you have 1 equals, and then on the right hand side we just plug in like regular, 2 to the 0 plus 1 minus 1. Okay, so this is the equation we're trying to prove, and what you want to do is simplify the left-hand side and the right-hand side separately and show that they equal the same number. So the left-hand side we don't have to do any work, that's just 1. And then the right-hand side is 2 to the 0 plus 1 minus 1, that's going to be 2 to the 1 minus 1, or just 2 minus 1, which is just 1. Okay. So the left-hand side equals the right-hand side. So that means that P of 0 is true. We have shown the equation is true when n equals 0. Okay, that's it. Now for our inductive step. Okay, so in this one, we will show that if P of k is true, then P of k plus 1 is true. So we're trying to prove an if-then statement, so just like we always do, we're going to assume that P of k is true. So assume the if part. Now don't just stop there, expand on that. What does it mean that P of k is true? So that means, what does it give you? So that means that 1 plus 2 squared plus ... up through 2 to the k equals 2 to the k plus 1 minus 1. So I'm just plugging in k for n, and then I think I abbreviated. I didn't include the 2 cubed, but that's in the dots. Okay, so that's what we get for our assumption. And now we need to show, so we will show that P of k plus 1 is true. So in other words, I'm going to expand what P of k plus 1 is. In other words, we will show, because we need to actually look at what it is we're trying to show, 1 plus 2 squared plus ... and now it's going to be k plus 1 up here, k plus 1 equals, okay, and now on the other side, be careful because you're plugging in k plus 1, so you're going to have k plus 1 minus 1. Okay, so this is the equation that we're trying to prove. And just like before, we're going to simplify the left-hand side and show that it actually equals the right-hand side. Okay, so let's start with the left-hand side. The left-hand side is, so now what I'm going to do is I'm going to rewrite it, and I'm going to pull one extra term out of the end of the dots. So the term that would have gone right before 2 to the k plus, the term that would have gone right before 2 to the k plus 1. The term right before that, that's abbreviated by the dots, is 2 to the k, because you know you have 2 to every integer. They just go along one by one. The exponent counts up. And so the next one then is 2 to the k plus 1. Okay, so I haven't done anything really. I've just pulled one term out of the dots. And so now what I can do is I can substitute for this part right here. I can substitute with this. Okay, so that is going to go there. All right, so this is going to become 2 to the k plus 1 minus 1 plus 2 to the k plus 1. Okay, now what can I do? Well, it looks like I have 2 copies of 2 to the k plus 1, so that's going to be 2 times 2 to the k plus 1 minus 1. Okay, and whenever I have 2 to an exponent times 2 to another exponent, I can write that as 2 to the 1 times 2 to the k plus 1 minus 1, and then I can add those exponents together. So this is going to be 2 to the k plus 1 minus 1. Oh, that's exactly the right-hand side. So that is the right-hand side of the equation that we were trying to prove. So the equation is true, and P of k plus 1 is true. And that's it. Okay, let's do another one. So this time it's not a summation type, it's a divisibility type. So these are kind of fun. Okay, so just like with the last two, we start off by defining the statement P of n. So let P of n stand for the following statement: 2 to the 2n minus 1 is divisible by 3. Okay, so for our basis step, we will show that P of 0 is true. So again, I'm just using that value that was right there. Okay, so in other words, let me expand what that means. What are we exactly trying to show? In other words, we will show that. So 2, so I'm just replacing what p of 0 is with the definition of that p thing. So 2 to the 2 times 0 minus 1 is divisible by 3. Okay, so that's our goal. And now to do that, I just need to figure out exactly what is 2 to the 2 times 0 minus 1. Okay, so 2 to the 2 times 0 minus 1 equals, let's see, that's 2 to the 0 minus 1, so that's 1 minus 1, oh, that's 0. So 0 is divisible by 3 because 0 equals 3 times 0. Okay, so if 0 can be factored into 3 and another integer, that means it's divisible by 3. Okay, so now the inductive step. Okay, so we will show that if p of k is true, then p of k plus 1 is true. So just like any other inductive proof, we're going to assume p of k is true. Okay, and now what does that mean? So for p of k to be true, that actually means, in other words, 2 to the 2k minus 1 is divisible by 3. So this is what we're assuming, and this is the information that we're going to be using later on. Okay, so now we need to show, now we will show p of k plus 1 is true. And let's just expand what that actually means. What are we exactly trying to show? In other words, that 2 to the 2 times, careful that you use parentheses here, minus 1, is divisible by 3. Okay, so that's what we have to show. Alright, so we're trying to show that 2 to the 2 times k plus 1 minus 1 is divisible by 3, and really the only thing we have that we can use is that 2 to the 2k minus 1 is divisible by 3. So I think actually what we should probably do is, probably what I should have done is, maybe back at this point, sorry, I'm just going to erase this. I probably should have gone a little deeper on what p of k exactly meant, so let me do that now. Oops. Okay, by 3. So what it means for 2 to the 2k minus 1 to be divisible by 3 is there exists some integer, I guess I'll call it q, so there exists an integer q such that 2 to the 2k minus 1 equals 3q. Okay, so I think this is going to be more helpful to me. So now let me go back to what I was talking about. So now we will show that p of k plus 1 is true. In other words, that 2 to the 2 times k plus 1 minus 1 is divisible by 3. Okay, so what we have to do is we have to find that 2 to the 2k plus 1 minus 1. We have to actually find that we can replace that with something that is 3 times an integer. Okay, so we're going to need to do some algebra to it. So what I'm going to do is I'm just going to write it 2k plus 1 minus 1, and I'm just going to try to like simplify it a little bit. And what I'm really looking for is I want to be able to use my assumption about 3q being 2 to the 2k minus 1. So at some point I would really like it if 2 to the 2k could appear here, and I can make that happen pretty easily. Let me show you how. So I'm going to distribute the parentheses like that, and then I'm going to split this up like this. So this is going to be 2 to the 2k times 2 to the 2. So that's just rules of exponents. And now I'm going to replace 2 to the 2k by 3q plus 1. Okay, so where is that coming from? That's coming from this. Okay, so if I just move the 1 over to the other right-hand side there, then I can make that substitution. So this is 4 times 3q plus 1 minus 1. Okay, so now I don't have any more exponents, which is great. So I'm just going to simplify this a little bit more. So this will be 12q plus 4 minus 1. Okay, and now you can really see that this is really going to be divisible by 3 because I can factor a 3 out of it. So this will be 4q plus 1. Okay, and now all I have to do is just argue that 4q plus 1 is an integer. So I'm just going to say since q is in the integers, 4q plus 1 is in the integers. So this shows me that 3 divides 2 to the 2k plus 1 minus 1, because I was able to write it as 3 times an integer. That means it's divisible by 3. And that's it. Okay, let's do one more of this divisibility type. So proof. So again, I'm going to start off by defining my p of n statement. So I should say let p of n stand for n cubed minus n is divisible by 6. Okay, so for the basis step, we will show that p of 0 is true. Okay, and now let me just expand on what I mean by p of 0. So in other words, we will show that 0 cubed minus 0 is divisible by 6. Okay, so this is not very hard to do because 0 cubed minus 0 is 0, which is divisible by 6 because 0 can be factored into 0 times 6. So if you can factor 0 into 6 times another integer, then that means it's divisible by 6. Okay, now the inductive step. So we will show if p of k is true, then p of k plus 1 is true. Okay, so we're going to assume p of k is true. So this is direct proof. All right, and now let's expand on that a little more. That means, what does that tell us? What kind of information does it give us to use? So that gives us this information that k cubed minus k is divisible by 6. And then expanding on that even further, I want to get all the way to an equation because that will be the best, most powerful type of information. So that means there exists some integer, I'll just call it q again because I'm not very creative. There exists q and z such that k cubed minus k equals 6q. Okay, so now what we need to show, we're going to show that p of k plus 1 is true. In other words, that k plus 1 cubed minus k plus 1 is divisible by 6. Okay, so in order to do this, the only thing I have that's really useful is the fact that k cubed minus k equals 6q. So I'm going to have to somehow make either k cubed or k to appear in the quantity that I'm working with. So let me just go ahead and start trying to simplify. So k plus 1 cubed minus k plus 1. So this is a little tricky to simplify, but I'm going to do it as k plus 1 squared times k plus 1 minus k plus 1. Okay, so this is going to be, you know what, actually what might be easier is if I factor a k plus 1 out of both terms. Let me try doing that instead. So k plus 1 times, then I'm going to have k plus 1 squared, and then minus 1. Okay, I think that might be easier. So let's do, this is k plus 1. Oops, sorry. Okay, and then I'm going to square, so I'm going to get k squared plus 2k plus 1 minus 1. Those are going to cancel. So this is going to be k plus 1 times k squared plus 2k. Okay, and now, again, the only thing I have that I can really work with is this, that k cubed minus k is 6q. So I'd really like to see a k cubed appear somewhere, and then I can replace it. So I'm going to go ahead and FOIL this out. So this is going to give me k cubed, and then let's see, k squared, and then another 2k squared, and then 2k. All right, let me simplify that. So this is going to be k cubed plus 3k squared plus 2k. Okay, so I see that k cubed, so that's what I'm going to aim to replace. So I'm going to replace k cubed with 6q plus k, and that is coming from here. Okay, it's coming from that equation there. So all I've done is just move the k over to the right-hand side, and then I have k cubed equals 6q plus k. All right, and then I'm going to have 3k squared plus 2k. Okay, so now let me just simplify a little more. So this is going to be 6q plus 3k squared plus 3k. Okay, so now I'm not exactly seeing a 6, but let me, at least not in the part with the 3's, but let me just keep simplifying a little bit and I'll show you what happens. So I can take out a 3k here, and I'm left with k plus 1. Okay, so now I have to do something a little bit clever to argue that this second term here, 3k, k plus 1, is actually divisible by 6. So let me try to convince you of that. So I'm going to say the following. Since k and k plus 1 are consecutive numbers, that means one of them has to be even. So they're consecutive integers, that means one of them has to be even. Like consecutive integers are like 2 and 3, or 3 and 4, or 4 and 5. One of them has to be even. So that means that product there, k times k plus 1, is even. That means that product is even also. So if k times k plus 1 is even, there exists some other integer, let's call it, I don't know, j. So there exists an integer j such that k times k plus 1 equals 2j. That's what it means to be even. Okay? So now I'm going to use that, and I'm going to substitute back in. And so what I have is 6q plus 3k k plus 1 is equal to 6q plus 3 times 2j. So that's 6q plus 6j. So now I can really see that this is divisible by 6 because it's 6 times q plus j. Okay, so since q plus j is an integer, I think that's pretty obvious. I defined q and j as both being integers. This means that 6 divides what we started with originally, which was k plus 1 cubed minus k plus 1. So P of k plus 1 is true. Okay, so this was definitely the hardest one, but I think it's not too bad. Okay, let's do part 4, recursive sequences, and there will be 2 questions like this on the test. Okay, so for the first part, we just have to find the first 3 terms of each sequence. So let's do number 1. So for number 1, we have that A0 is 0 and A1 is 1. So we want to find the next 3. That means A2, A3, and A4. So how are we going to get A2? So if I want A2, I have to use this formula here that tells me the value of any A. So I'm using n equals 2. So this is going to be using n equals 2. So basically I'm just plugging n equals 2 into that formula. So then I'll get A2 equals 3 times A2 minus 1 plus A2 minus 2. Okay, so that's going to be 3 times A1, so 2 minus 1 is 1, plus A0. 2 minus 2 is 0. Okay, so you just have to do a little bit of arithmetic down in those subscripts, but you're just plugging in n equals 2 there. And so now I know what A1 and A0 are. So this is 1, and this one is 0. So this is going to be 3. All right, then for A3, I'm going to be using n equals 3. So I'm just plugging in 3 for all my n's here. So this is going to be A sub 3 minus 1, and then plus A sub 3 minus 2. So that is 3 times A2 plus A1. So I know what A2 and A1 are because I just worked out A2. So this is going to be 3 times, so A2 is 3, and then A1 is 1. So this is going to be 10. And then finally A4, so here I'm using n equals 4. So A4 is going to be 3 times A4 minus 1 plus A4 minus 2. So that's going to be 3A3 plus A2. And again, I just worked out what some of those were. So this one is 10. It's the one I just worked out. And then the one before that, A2 was 3. So this is going to be 33. Okay, let's do number 2. So same process. This time you do have the plus 1 over here, so you have to be a little bit careful about exactly which values you're going to plug in for I. But we do have B1 equals 3, B2 equals 4, so we're going to be trying to get B3, B4, and B5. Okay, so I want to have B3, so that means for I, since I'm using B sub I plus 1, my I needs to be 2. So this is using I equals 2. When I plug in I equals 2, I get B3 on the left, and then on the right, I get B2. That's just I. And then this one will be B1. Okay, so I know what B2 and B1 are. So this is just 4, and this one is 3. So this is 1. And then if I want to get B4, then I need to use I equals 3. So when I plug in I equals 3 to those subscripts, this becomes B4, it's I plus 1, and then this one will be just BI, that's B3, and then BI minus 1, I minus 1 is 2. Okay, so this will be, let's see, I just did B3, that was 1, and then B2 was given, that was 4, so this is negative 3. And then finally, oops, to get B5, I need to use I equals 4. Okay, so then when I plug in I equals 4, I plus 1 will be 5, so this will be B5. And then this one will be B4. And then I minus 1 will be 3, so this will be B3. Okay, so this will be B4 was negative 3, and then B3 was 1, so this will be negative 4. All right, and I'll do 3 on the next slide. Okay, so number 3. All right, so they gave me C0 is 1, C1 is 2, and so for C2, we're going to need to plug in j equals 2. So that's on the left hand side, I have just cj, so I can use j equals 2. Okay, so then this is going to be, let's see, j minus 1 is 1, so that'll be c1. And then on the bottom, j minus 1 again, so that's c1 again, plus 1. So c1 was 2, so this will be 2 over 2 plus 1, which is 2/3. Okay, and then c3, so for c3 I'm using j equals 3. Okay, and then on the right hand side, j minus 1 will be 2, so this is going to be c2 over c2 plus 1. So this is 2/3 over 2/3 plus 1. So 2/3 plus 1 is 5/3. So this will be 2/3 times 3/5. That's 2/5. Okay, and then c4, I'm using j equals 4. So this will be c4, and then j minus 1 is 3, so this will be c3, and then c3 plus 1. Okay, so this is 2/5 over 2/5 plus 1. I think 2/5 plus 1 is 7/5. So then this is going to be 2 over 5 times 7, times 5 over 7. So the 5's cancel, and that gives me 2/7. And that's it. Okay, so now let's talk about checking whether an explicit formula matches a recurrence relation. So I have here 6 explicit formulas, and each of these explicit formulas satisfies one or more of these 3 recurrence relations. So let's go ahead and check them all. So let me do number 1. So I'm going to check 1 against recurrence relation A. And actually, I think what I want to do before I do any of these is I'm going to figure out what an would be, what an minus 1 would be, and what an minus 2 would be. Okay, so for number 1, using the formula for ak, that would make an. So you're plugging in n for k. Okay, so that would make an 2 to the n. And then an minus 1. So you're plugging in n minus 1 instead of k. So that would be 2 to the n minus 1. And then finally an minus 2. So you're plugging in n minus 2 for k. So that would give you 2 to the n minus 2. So let's just check a, b, and c. So let's check A. Okay, so does 2 to the n, so I'm going to use a little question mark here, does that equal 2 times 2 to the n minus 1 minus 2 to the n minus 2? So you see I just plugged in the values that I just found for an minus 1, and an minus 2 into that recurrence relation. And then I put a question mark over the equal sign there because I'm not sure. So this will be 2 to the n, and then the right-hand side, I can simplify it as, this is 2 to the 1 times 2 to the n minus 1, minus 2 to the n minus 2. So this will be 2 to the n, if I just add those exponents together, minus 2 to the n minus 2. So I don't, those are definitely not equal. So I could cancel the 2 to the n, for example, and then I would have 0 equals negative 2 to the n minus 2. So this is a no. All right, and then let's check B. So I'm just going to plug in these terms again. So a to an was 2 to the n, and then does that equal an minus 1, and then plus 2 times 2 to the n minus 2. Okay, so this time I think this might actually work out. So this is going to be 2 to the n minus 1, and then this one I can write that as 2 to the n minus 1, because this is 2 to the 1 here, and then I can add the exponents together, and then what I've really got is 2 times 2 to the n minus 1. So I can do the same process again and add the exponents together, and this will be 2 to the n. Okay, so this one actually does work. So that's a yes. Okay, and then I'll check recurrence relation C. I'll check that on the next slide. Okay, so let's look at the third recurrence relation here, and this is actually a typo. This was supposed to say 1 right here, so that's supposed to be a 1. All right, so let's check C. Okay, so I'm just going to plug these in again. So an is 2 to the n, and then I'm going to put an equals with a question mark because I don't know if it's equal, and then 3 times 2n minus 1, and then minus 2 times an minus 2. Okay, so we just have to check if this is true or not. So left-hand side stays like that. Right-hand side I can simplify maybe a little bit. Let's see, 3 times 2 n minus 1, that'll stay the same. And then here I'm going to combine the 2's, so this will be 2 to the n minus 1. So I'm adding the exponents of the 2's together. And then I've got 3 to n to the minus, or sorry, I've got 3 copies of 2 to the n minus 1 minus 1 copy of 2 to the n minus 1. So that is something I can factor. So I've got 2 to the n minus 1. I've got 3 copies of it minus 1 copy of it, like that. Okay, and then that can be simplified like this. So there I can add the exponents of the 2's together again, and I actually get that this is equal. So n minus 1 plus 1 is n. So this is a yes. So this one, excuse me, it satisfied both B and C. So that's actually kind of interesting that the same explicit formula can satisfy more than one different recurrence relation. Okay, let's look at number 2. Okay, so for number 2, again, I'm just going to write out what an minus 1, and an minus 2 would be. So this one will be just n, and then an minus 1, so I'm plugging in n minus 1 for k, so that's that, and then an minus 2, plugging in n minus 2 for k this time, so that's that. Okay, so let's check A, B, and C. So on the left I have n, and then I have a question equals, and then on the right I have 2 times an minus 1 minus an minus 2. And let's see, so this will be 2n minus 2 minus n plus 2. So actually this does work out. So this is going to be, that's going to cancel, and then that leaves me with n there, so this is a yes. And now let's check B. So on the left I have an, and then on the right I have an minus 1 plus 2 times an minus 2. So let's see, this is going to be n minus 1 plus 2n minus 4. So I think that is not going to work out, because that'll be 3n minus 5, which is not equal to n in general. So this is a no. Okay, and then let's check C. So on the left I have an, and then on the right I have again this is a typo, so this is supposed to be 1. So this will be n minus 1, and then minus 2 an minus 2, which is that. And then we're checking this, so I'll put the question mark. So this is going to be 3n minus 3 minus 2n plus 4. So this will be in all, let's see, we have 1 copy of n and then plus 1. So this is a no. Okay, let's do number 3. So I'm going to figure out what an minus 1 and an minus 2 are. So an will just be 2n, plugging in n for k, and then plugging in n minus 1 for k, I'm going to get 2 times n minus 1, which is 2n minus 2, and then for an minus 2, same deal, but with n minus 2, so this will be 2n minus 4. Okay. And let's just check these 3 recurrence relations. So the first one I'm checking, does 2n equal, so 2 times an minus 1, and then minus an an minus 2, so this will be minus 2n minus 4. Okay, let's distribute. So this will be 4n minus 4 minus 2n plus 4. So the 4's cancel, but we still have 2n over here on the right. Oh, and we do have 2n on the left. Oh, okay, so yeah, this does work. So this is a yes. Now let's check B. So on the left we have an, which is 2n, and on the right we have an minus 1, and then plus 2 times an minus 2. So just simplifying. So I think this one is not going to work out because this is going to be 6n minus 10, which is not the same as 2n. So this is a no. And then let's check C. So again, this was a typo, so that's supposed to say 1. So an is 2n, and then 3 times an minus 1, which is 2n minus 2, and then minus 2 times an minus 2, which is that. Okay, so I'm just going to simplify 6n minus 6 minus 4n plus 8. So this is going to be, let's see, I'm going to have 2 n's and plus 2. So that is not the same. Okay, let's do number 4. So again, I'll just write out what an would be. So that's plugging in n for k, and then plugging in n minus 1 for k, and then finally plugging in n minus 2 for k. Alrighty, so let's check A, B, and C. So on the left I have an, and on the right I have an minus 1 times 2, and then minus an minus 2. Okay, so this is maybe a little bit tricky, but what I can do here is I can rewrite, so it's a question mark there, I can rewrite the minus as plus -1 times -1 to the n minus 2, and then I can add the exponents there together, so this is -1 to the 1, and then 1 plus n minus 2 is going to give me this, so 2 times that. So this will be -1 to the n minus 1, so 1 plus n minus 2 is n minus 1, and then I have 2 copies of -1 to the n minus 1 plus another copy of -1 to the n minus 1, so that is actually 3 times -1 to the n minus 1, so that is not the same, so this is a no. Alright, and now let's check B. So on the left I have an minus 1, and on the right I have an minus 1, and then plus 2 times -1 to the n minus 2. Okay, so this is probably the trickiest one of all, and maybe it's too tricky that I shouldn't have even put it. But what you can actually do here on the right is you can split this 2 coefficient up like this, so you can have one copy of -1 to the n minus 2 and then another copy of it. And then what you could do is, because n minus 1 and n minus 2 are consecutive, you can just argue that one of these, oops, one of these is 1 and the other is -1. So -1 raised to any power is going to alternate between 1 and -1, and so if those exponents are 1 off like that, then one of those two will always be 1 and the other one will be a -1. So those are going to cancel out, basically. So this is just going to be -1 to the n minus 2 here. And then what I want you to notice is that n and n minus 2 are always either both even or both odd. So when you're thinking about that alternation thing, when -1 is to an even power, then it's 1, and when it's to an odd power, then it is -1. So these actually are going to be equal, although that's a little maybe hard to see. Maybe I could convince you a little bit more of that if I do the following. So let me go over here, actually. So I'll have to do C on another slide. So I can write -1 to the n. So let me just copy what I had. Okay, so this is like that. Okay, so let me do the following. I can split off the -2 part. So this will be -2 over here, like this. Okay, and then I can simplify that that part. So this will be 1 over -2 squared. That's what the -2 power means. And then that is just 1. Okay, so this part right here is just 1. So that's going to cancel. And then this will just be -1 to the n. Okay, maybe that's a better way to show it. So this is actually going to be a yes. Okay, and then I will do C on the next slide. Okay, so now let's check C. Okay, so the left side of C, and again this was a typo, so the left side will be -1 to the n, and then we're checking if that equals -1 to the n minus 1, oops, I forgot the 3, minus 2 times -1 to the n minus 2. Okay, so I think what I did in the last part was actually a pretty good way of approaching this, so let me try using that little trick again, where I split off the powers like this. So I'll make that n, and then -1 to another -1 power, and then -2, -1 to the n, -1 to the -2. Okay, so we already saw that this -1 to the -2, that's just going to be, oops, sorry. That's just going to be 1, so that's going to cancel. And this -1 to the -1, that's going to be -1. So what's going to happen here? I'm going to have actually 3 -1 to the n times -1, and then -2 times -1 to the n. So let's see. Let me come over here. So this is going to be -1 to the n is still on the right, or on the left, sorry. Getting all mixed up. And then I can make this -3 times -1 to the n, minus 2 times -1 to the n. Okay, I think you're seeing here this is going to be -5 to the times -1 to the n. So this is going to be a no. Okay, let's do number 5. So again, I'm just going to check what an is. That's 3n plus 1, and then an minus 1 is going to be 3 times n minus 1 plus 1. So I can simplify that to 3n minus 2, and then an minus 2 is going to be 3n minus 2 plus 1. So that will be 3n minus 5. Okay, so now let's check A. So I'm checking, does an equal 2 times an minus 1 minus an minus 2? Okay, so I'm just going to simplify the right-hand side. So this is 6n minus 4 minus 3n plus 5. So I get 3n plus 1, so that's a yes. Now let's check B. So here I'm checking if an equals an minus 1 plus 2 times an minus 2. So that's going to be, that stays the same, and then this is going to be 6n minus 10, and then this will become 9n minus 12, so that's a no. And then finally, for part C, I'm checking if an equals 3 times, and this was a typo again, so this is 3n minus 2 minus 2 times an minus 2. So that's going to be 9n minus 6 minus 6n plus 10. So this is going to leave me with 3n plus 4, so that's going to be another no. Okay. Okay, so number 6 is the easiest of all to check because an is 1, an minus 1 is 1, and an minus 2 is also 1. It's always just 1. Okay, so let's check A. So does 1 equal 2 times 1 minus 1? So that's a yes. And then let's check B. So does 1 equal 1 plus 2 times 1? So on the right we're going to get 3, so that's a no. And then finally, let's check C. So does 1 equal 3 times 1 minus 2 times 1? So that is going to be a yes. Okay,